Hello and welcome to this Raven version 3 tutorial. In this tutorial, I will demonstrate how to perform a 1D thermochemical analysis of a composite material during its manufacturing cycle. This type of simulation can be used to analyze the temperature distribution through the thickness of a composite part laid up on a tool. This simulation is performed along a one-dimensional line through the thickness of the composite part and tool layup, what we call a drill-through analysis. To perform this simulation, I will go under the 1D tab in the task pane and select the Thermal Profile Study link. This brings up the Create New Thermal Profile Study dialog box. I'll open a previously created stack. Here I have a visual representation of the one-dimensional through-thickness drill-through, including the relative thickness of each component. First, I have an aluminum tool at 25 mm thick. Then I have a composite part at 5 mm thick. And finally, I have a breather cloth at 1 mm thick. In addition to the materials, I have defined boundary conditions. On the top and bottom, I have heat transfer boundary conditions with a heat transfer coefficient of 30 watts per meter squared Kelvin. I have also defined the location for Z equals 0, with Z being the through thickness axis. Using the buttons in the middle of the dialog box, I can create and manage my stack. So, for example, I can add a new boundary or material, move it up or down in the stack, or delete the boundary of a material. The properties of each layer in the stack can be edited when that layer is selected. So for example, I can change the thickness of the aluminum tool by selecting the aluminum layer and editing the thickness. Notice the relative thickness of the diagram on the right changes as well. Once I've defined the stack, I need to define the main cycle. This is the autoclave or oven air temperature cycle of the air above and below the stack. In this case, I have a ramp of 1 C per minute to 107 C, a hold for 60 minutes, a second ramp to 135 C at 1 C per minute, and a cool to 20 C at 1 C per minute. I now have everything I need to run a 1D thermochemical and heat transfer analysis. I define the materials in the stack and their thicknesses, I define the heat transfer boundary conditions, and I define the temperature cycle of the surrounding air. In the Post-Processing tab, I can specify which plots I want to have Raven produce when I run the analysis. I can always create these plots later, but it's convenient to have Raven create them automatically. In general, I can create plots of any variable versus time or versus through thickness distance. For now, I have created a plot of temperature versus time, and by clicking OK, Raven will run the analysis. The default temperature versus time plot shows temperature history at the top, bottom, and middle of each layer of the stack. I'll turn off the breather in aluminum to investigate the part temperature only. We can see that during heat up, there's a significant temperature lag between the air temperature and the temperature of the part. There's also an overshoot of the part temperature due to the exothermic reaction of the cure, and we can see that there's a small thermal gradient through the thickness of the part. Note that any point through the thickness of the part is also available to plot. We can also plot material properties for any point through the thickness. For example, I can add a new series to this plot. Select the top, middle, and bottom layers, and plot the degree of cure versus time. There are many other powerful investigations we can perform with Raven 1D thermochemical heat transfer analysis. For example, we can investigate the effect of using different tooling materials or different tooling thicknesses by simply altering the defined layout. We can also perform an array of 1D analyses representing various regions of a 3D part. Thank you for watching this video tutorial. If you have any further questions or interest in composites processing, please do not hesitate to contact us or visit our website at convergent.ca.